Okay, section 4, last section for the week. We are doing 1.4, continuity and one-sided limits. Okay, here is a definition of continuity out of your textbook. All these definitions, and if you do theorems, they're all out of your textbook, so they can be kind of useful. We're talking about continuity at a single location at a point. That point in this is going to be C. So function f is continuous at C when three conditions are met. So when the function exists at C, so when I plug C in, it exists. Okay, that means it's continuous. If its limit as it approaches C, which is different because we saw last section that it can approach a value, which is the limit, and it can equal a different value. Okay, but they're approaching and equal to the same value. That is met, and then when I plug it in, I get exactly that output. Okay, so 3 kind of combines 1 and 2 together. So that means it's continuous. Essentially, continuous is when I pick up my pen, when I trace the graph, my pencil is not picked up. It is continuous. I don't have to go over or skip or jump or anything like that. There's no holes in my graph. There's no jumps in my graph. There's no asymptotes in my graph. A function is continuous on an open interval AB when the function is continuous at every single point in that interval. That is common sense. A function is continuous on an entire real number line if it's continuous everywhere. So sometimes we'll see it's continuous in a specific range, or in this case, a domain. It's not continuous everywhere, but it is continuous in certain restraints. Okay, there are 2 types of discontinuities. They are important. Removable means that I can do factoring, manipulation, division of some sort, and then the limit will exist. It doesn't exist I can't just plug the number in as it is, but I can manipulate it and the limit exists. So the function may not exist, but the limit may exist. That's a removable discontinuity. Like some of the ones when we simplify the limit on last section by factoring and canceling out the denominator, that would be an example of a removable discontinuity. A non-removable discontinuity would mean it's just not continuous. Okay. All right, so we're just going to look at the discontinuity of these 5 different functions. Okay, first one, if you look, it should be obvious as to what or where it's discontinuous at, but think of things that make things discontinuous, like you can't divide by 0, you can't take roots of negative numbers, things like that, that will restrict your domain. So domain and continuity go hand in hand. Okay, so we know by looking at this, x cannot be 0, okay, because I can't divide by 0. So it has, and I can't manipulate it, I can't back top, I can't cancel it out. So this would be considered a non-removable discontinuity. At x equals 0. Okay, since it can't be that, therefore it has a non-removable, and I can't do any factoring to it. This one, if you notice, x can't be 1 from the beginning, but if you notice the numerator of this factors into x plus 1 and x minus 1, it's a difference of 2 squares. Okay, and the bottom is still x minus 1. And since I can cancel it and get x plus 1, that allows me to plug in 1. So I couldn't plug in 1 originally, but the limit does exist at 1. So that would be what we call a removable discontinuity. At x equals 1. Okay. This is a piecewise function. Sometimes piecewise functions, the sections will overlap and connect, and that would make them continuous. And sometimes they have a disconnect, and sometimes they're not continuous. So what I look at is if I were to think of things where they're equal to and where it's not. So here's an interesting thing. At 0 here, okay, h of x equals 1. Okay, my equal sign looks rough. Equals 1. Okay, that's important. And then if you think of that as it gets closer and closer and closer to 0, it's going to be certain things. And as it gets farther and farther and farther away from 0, it is going to be something different entirely. So when you look at these piecewise functions, you have to look at the sections of it. Okay. And this is an error. This should be e to the power of x. Okay. And so then here at 0, h of x, and I know it's not equal to 0, it's greater than 0, but if you're trying to get infinitesimally close to it, it's approaching what value? It's going to approach the value when I plug in 0. So you're looking basically at the limit of h of x instead of actual h of x. Okay. So this is the limit as h approaches x. It's going to be equal to e to the 0, which is also 1. So this fills in everywhere this one was. So it's continuous everywhere because they connect. So you can say like all real numbers or whatever, and I'm going to put the explanation, they connect, so if you look back at your notes, you understand why. Okay, y equals sine x. This one, you can go and plug in a bajillion 12 numbers, but really based off your pre-calculus information, you should just know that this graph, it looks like this forever and ever and ever and ever, except way more symmetric and not as goofy looking as mine, but it constantly goes left, constantly goes right. There's no asymptotes, there's no holes, so it's continuous. I don't know if you guys know the symbol for all real numbers, but you can actually write all real numbers like that. That's the same thing as negative infinity to infinity. They are interchangeable. Or you can just write the statement all real numbers. And this next one, square roots often imply a restricted domain. So I know that underneath that square root has to be greater than or equal to 0. Okay, that's really, really important. Okay, so I have to figure out what happens. So what I'm going to do is I'm going to solve for x. I'm going to move x to the other side, so I get this, which is an interesting concept there. And if I were to square root both sides, you have to remember, a lot of you, almost everybody, I think, but one person missed this on their test, but when you square root or even root both sides of an equation, you have to do plus or minus. So that's a weird concept, because how can I have x is less than positive and negative 1? Well, you can't. So you would actually have to test what's going on around 1. So if I have a number line on 1, I'm going to pick a number to the left of 1, say 0, and a number to the right of 1, say 2, and I'm going to figure out what's true or false. Okay, so if I plug this in, so I'm looking at the true and false of plugging in 0, and then I'll be able to know. So is x less than or equal to 1 if I pick 0? Well, 0 is less than or equal to 1. Okay, so that's true. Okay, and then if I plug in 2, is 2 less than or equal to 1? No, that's false. And I should have put a little more room for negative 1 here. And then I would pick, we'll pick negative 2 for the left of that. And I'll do negative 2 is 1 less than or equal to negative 2. Okay, or 1 is greater than. And that is true. Okay, so we're going to look at this. And what that means is that it is true when it's in between. Okay, it is true when it's in between. That's negative 1. Okay, so it's true here, and it's false everywhere else. So that means that I have negative 1 is less than or equal to x is less than or equal to 1. That would be your domain. That's it. So it fits in between that. So you're looking at true and false as you examine that. Okay, be careful with things like that. It can be a little hard. Might help to graph it. Oops, sorry, that's sleepy. All right, find the limit of f of x as a square root of 4 or minus x squared as x approaches negative 2 from the right. So here's a concept. So that little plus sign there is really important. So you're just looking at it from the right. That is all. So I don't care as it approaches from both sides. I care as it approaches specifically from the right. Okay, so what that means is we are going to be looking at all the values. Sometimes they jump, and it may be different from the right and from the left, which means it's not continuous everywhere, but it might be continuous right there, or the limit doesn't exist everywhere, but it exists on the right and it exists on the left. They just don't go together. And so what I'm going to do is kind of think about, instead of x approaching negative 2, which I can plug in negative 2, and I'm going to get 0. but I want to think about it really, really, really close to that value so that I know what exactly it is going to be approaching. And so I'm going to actually think about this. You're not thinking of -2 exactly. You're thinking to the right of -2. So on a number line to the right of -2 would be like -1.9999, and we could go on for a while. Okay. And I'm thinking of that. So the farther out I go, the closer it's going to be to 2. And you will get something for minus close to 2. I know that seems silly, but we're going to have some weird math going on. Squared. And so you're going to end up with square root of 4 minus close to 4. Okay, because again, you're not doing f of that value, you're doing close to it, you're doing the limit, and that is equal to 0. Okay, so it seems like weird math, I understand that, but that's a good way to start thinking about things, is you can think of just sections of things, okay, as they're getting close to numbers. Okay, so that kind of leads us into this example. So greatest integer function, I'm not sure if that's something you've ever taught. Basically, that is your rounding up function. Okay, so and then the lowest integer function would be your rounding down function. Okay, it is denoted by like these double brackets, or sometimes it's noted by, if it's a rounding up function, it's kind of like they have hats on them. Like this, it's just the top part of the bracket. A rounding down fraction, you would have almost like L's, and backwards L's would be just the bottom part of it. Okay, so that you're just rounding up. So if I were to plug in, say, 1.5 into greatest integer function, it's actually 2. The output would be. If I plug in 1.9, it's also 2. If I plug in 1.001, it's still 2 because it's a rounding up function. It just rounds up no matter what. Okay, so we're going to look at 2 limits. We're going to look at the limit as x approaches 0 from the right of my greatest integer function. And then we're going to look at the limit as x approaches 0 from the left of my greatest integer function. So let's first just look at this general function, since one, it's probably a super new idea to all of you. If I have a basic coordinate plane and I were graphing the greatest integer function it is, basically it's saying everything is going to round up. So, for example, at, what were we saying earlier? At 1, it's going to be 1. At 2, it's going to be 2 because, we're rounding up, and so those are exact, so it's not rounding at that point. So these are going to be exact. But then anything from here to here is going to round up, okay? So if I'm doing it this way, then at -1, or at 1, it's going to be going up to, or at 0, it's going to be going up to 1, or rounding. Okay, and then here it's going to be going here, and here it's going, so it makes what they call a step function. Okay, so that anything at a given value is going to be rounded up. Okay, so it's all going to be going up, and we're looking at as it's approaching from one side to the other side. So as it's approaching from the right, it's approaching 0. Okay, as it's approaching from the left, it's approaching -1. You're looking at the output. So as it's approaching from the right, it's approaching 0. And as it's approaching from the left, it's approaching -1, which is why it's not continuous. They don't overlap. But it makes an interesting concept. Within those individual intervals, it is continuous, but it wouldn't be continuous. And that's not what it's asking for before connecting to what we previously talked for. And so those are those 2 different limits. And that's the reason they're not continuous, is because they're not the same value. It has to be the same from the right and the left to be continuous. That's just an interesting concept. You'll see a couple problems like that possibly, and to me it helps to graph them. All right, sorry this is a little blurry. Just a note, I couldn't get rid of the QR code, but it's a good reminder that in your textbook there are QR codes that you can scan for helpful videos or for further examples. All right, so properties of continuity. If I have a continuous function f and g, and then there's some constant value c, where x is c, and it's continuous at c. If I multiply a continuous function by a scalar, which is just, again, like multiply by 2 or multiply by 1/2. So like number 1, it's still going to be continuous. If I add two continuous functions like number 2, still continuous, add or subtract. If I multiply two continuous functions, it's still continuous. And if I divide continuous functions, it's still continuous as long as the denominator is not equal to 0. Okay, that is straight out of your textbook. We are going to now describe the intervals for each function is going to be continuous as well. All right, so if we're looking at the function tangent, if you recall, tangent is a really interesting function in the sense that it has quite a few asymptotes because tangent is sine over cosine. So anywhere that cosine is equal to 0, okay, so we look at our unit circle, anywhere cosine is equal to 0, which is here and here, tangent is undefined because there's going to be an asymptote there because it's sine over cosine. And so as many times as we go around, forever and ever and ever, it's going to be that way. So if we kind of look like the initial around that we were used to would be like negative pi over 2 to pi over 2. Okay, pi over 2 being this top guy. Negative pi over 2 would be going the other direction here. And if I did that again and again and again, either direction, that's going to give you all of that domain. So the domain is continuous everywhere. If you're talking about where it's continuous, I'll abbreviate, everywhere, except any repetition of those values. Well, how do we note that? We can say it's pi over 2. And then if you think about how did I get from pi over 2 to negative pi, I subtracted a whole pi. Okay. And then if you wanted to think, you could also go the other direction with these where you go pi over 2 and you continue another pi, 3 over pi over 2, or you could go backwards where you're going to go from negative pi over 2 to negative 3 pi over 2 because you can go around. It didn't restrict how many times you go around. So in order to get all of those values, I'll just do plus n pi. And n can be a negative whole number or a positive whole number. We'll just call it an integer. And that would encompass all of those. All right. G of x, we're looking at where it's continuous. Obviously, I can't plug in 0 into sine x, but I can plug in anything before sine x or anything to the left of 0 and to the right of 0, and it would all work out. And this function here exists everywhere or is continuous everywhere except x equals 0. And this is x equals 0. So it doesn't connect and it doesn't approach a single value. We've already looked at this function here. That is that function that when we graphed it, it was like here in zigzaggy like that or something similar to that. And so it doesn't approach a single value. And this did not fill in the hole. Now what's interesting here is as x approaches 0 for this top function, so does f of x. The difference is that I'm multiplying now by a 0, which makes that whole function go to 0. Now, it still doesn't exist at 0, but it's getting infinitesimally close to 0. It is approaching. If you were to look at that graph, it would be really interesting if you plug that into your graphing calculator, just the x sine 1 over x. It would be getting really, really close to it because of that multiplying by x, and we are looking at x as it gets close to 0. And then x is actually 0 here, okay, when I plug it in. And so f of x would equal exactly 0 there. It fills in the gap that the one above creates. And so it is continuous actually everywhere. Okay, last concept is the intermediate value theorem. And the intermediate value theorem says if f is continuous on a closed interval, AB, meaning A is included, B is including, those brackets are important. If it wasn't included, it'd be parentheses. But they can't be the same value as the output. So f of A, when I plug it in, the y values can't be the same as f of B. Okay. And K is any number between f of A and f of B, meaning K is an output because f of B and f of A are both in the range. Okay. Then there's at least one value C in the domain. Okay. So there's some sort of X value in the domain such that f of C equals that K that's in the range. Okay. So I'm going to back that up and say it again because that is a weird theorem. There is some value K in the range, so a Y value. There's also some value C, an X value in the domain, so that when I plug the C value, it is that value K. Okay, that is the intermediate value theorem. The AP Calculus test loves the intermediate value theorem, so this would be one to put on your docket to memorize and practice prior to taking your AP test. Okay, so they call it the IVT for short. So you will not always see it referenced as intermediate value theorem. You'll use the intermediate value theorem. Okay, so use the intermediate value theorem to show that the polynomial f of x equals x cubed plus 2x plus 1 has a 0, meaning some sort of x value, in the closed interval 0 to 1. So what I want you to do is, 1, it has to be continuous. That's part of it. So if f is continuous, well, this is a cubic function. And so we know by characteristic it is continuous. It's a positive function because leading coefficient, and it's going to have ends going opposite direction because degree is this, and it has some sort of connectivity going on in the middle. Okay, if you want to graph it in your graphing calculator, look at it, you can see that it's continuous. It exists everywhere. Okay, there's no problems with domain where it's divided by a value or a square root, so it is continuous everywhere. All polynomials are continuous. Okay, and it has a 0, meaning an x value, an x-intercept in 0, 1. Okay, so what we want to look for first is it's talking about this. So we have our closed interval. We need to say this is A and this is B. If you follow the intermediate value theorem, that's what that would mean. So I need to look at f of A and f of B. In this case, that's f of 0 and f of 1. And just plug those in. So 0 is super easy to plug in. Well, both of them will be. I'll have 0 cubed plus 2 times 0 plus 1. So I get 1. And I will plug in 1. And I will get 1 cubed plus, which is 1 plus 2 plus 1. So I get 4. Okay. And so then that is important because we have to make sure, 1, they're not equal, which they're not. Okay. And that K is some value in between that. So what we're going to do is we're going to say let K, make that, be in the open interval, -1 to 2. I can't have it be equal to -1, and I can't have it be equal to 2. It's got to be some other value other than the endpoints, okay, of that range. Since there is a K value, since we have this range there, well, not -1 to 2, sorry, 1 to 4. Let K be in 1 to 4. Those are those numbers we just found. And that's a value that we're going to pick. There must exist, using the IVT, a C value in the closed interval. What'd they give me? 0 to 1. Okay. That's all I have to do is, because it satisfies the beginning, if that happens, then the other must happen. Okay, it's a conditional statement. So we were able to show that they don't exist and K is some value in between it. Therefore, there's at least some value C. It is that simple, and that's all you have to do. Okay, so you'd show these are not equal to each other. You say that K is in that interval as long as that is true. Therefore, there must exist. Okay, then is the conclusion of that statement. So if you can satisfy the first several things, you've satisfied the rest of it. All right. And that is the end of that, and homework will be posted with this.